Let's turn off the power supply and build our circuit of interest, and then use the DMM to measure voltage inside the circuit. Our circuit again consists of a 5-volt source and a 200 ohm resistor rated for low power applications of less than a quarter watt. A nominal 200 ohm resistor should have a 4-band resistor color code of red, black, brown, gold, meaning 20 followed by 10. Let's use the ohm meter function to verify if a resistor matching this description is inside the expected range. We need to take the DMM out of voltmeter mode and put it in ohm meter mode using the checklist to do so. Function, leads, range, placement. Given a plus or minus 5% tolerance, we should anticipate a low of 190 ohms up to a high of 210 ohms. When placed between the probes of the ohm meter, the nominal 200 ohm resistor appears to have a resistance inside our expected range. Let's put the DMM aside for now and build our circuit. A lead from the power supply red binding post positive terminal is landed on the protoboard red binding post. A lead from the power supply black negative binding post is landed on the protoboard black binding post. A wire from the protoboard red binding post is landed on node 5A through E. A wire from the protoboard black binding post is landed on node 5F through J across the ditch. One terminal of the nominal 200 ohm resistor is inserted into the collection of points constituting the node 5A through E, and the other terminal of the resistor is inserted into the collection of points constituting the node 5F through J across the ditch. The one and only path from node 5A through E to 5F through J is through the nominal 200 ohm resistor. A complete circuit has been established, and we can turn on the power supply. Let's use the DMM in DC voltmeter mode to measure the loaded voltage supplied by the source, meaning this is the voltage differential established by the source when it is providing current to load elements in the circuit. This is in contrast to the unloaded voltage or open circuit voltage which we measured previously. Ideally, we should observe roughly 5 volts. This necessitates we take the DMM out of ohm meter mode and put it back in DC voltmeter mode. Use the checklist to do so. Function, leads, range, placement. To measure the loaded voltage, the black common lead of the voltmeter is placed in the black negative terminal of the source, and the red lead on the red positive terminal of the source. As anticipated, we observe a voltage rise of roughly 5 volts. Let's now use the DC voltmeter to measure the voltage drop across the nominal 200 ohm resistor. There's a couple ways of measuring voltage drops across components inserted in a protoboard. Method 1. If the component is large enough, use a pair of clip leads directly connected to the component. The red lead of the voltmeter is clipped to one terminal of the resistor, landed at node 5A through E, and the black lead of the voltmeter is clipped to the other terminal of the resistor, landed at node 5F through J. We observe a voltage drop of roughly 5 volts from node 5A through E to node 5F through J, as we'd expect. Method 2. If space comes at a premium, use accessory wires with a pair of clip leads at the nodes of interest. The red lead accessory wire is directly plugged into node 5A through E, and the black lead accessory wire is plugged directly into node 5F through J. As previously, we observe a voltage drop of roughly 5 volts from node 5A through E to node 5F through J, as we'd expect. Easy, right? Yes. Voltmeters are super easy to use because it's easy to recognize that voltmeters are 2-point measurements across the terminals of interest. This being said, you can screw it up, and here's a couple ways you might do so. Be on the lookout for these mix-ups, and be smart enough to recognize them when they happen. Here's one way of screwing up voltage measurement. Voltage is a 2-point measurement. What if you measured voltage at the same point? Consider both leads of the voltmeter plugged into node 5A through E. The voltmeter demonstrates no voltage differential exists between node 5A through E and node 5A through E. One should hope so. They're the same point. This is not how you employ a DC voltmeter. Here's another way of taking a bad voltage measurement. Again, voltage is a 2-point measurement, and both these points need to be in the same circuit. Consider the red lead of the voltmeter plugged into node 5A through E, and the black lead dangling out in space or plugged into some isolated unconnected node. Any reading by this voltmeter is absolute nonsense because the reference lead isn't inside this circuit. Here's another way of taking a bad voltage measurement. Recall that voltage is dropped across a component only when current flows through it. If we include an open or missed connection in our circuit, no circuit exists, no current flows, and no voltage will be dropped across the opened element. Here the power supply positive connection is landed at node 2A through E, and the power supply negative connection is landed at node 5F through J. One terminal of the nominal 200 ohm resistor is landed at node 5A through E, and the other terminal of the nominal 200 ohm resistor is landed at node 5F through J. Note that no connection exists between node 2A through E and node 5A through E despite their close proximity. No circuit exists and no current flows. We should anticipate no voltage drop. As we anticipated, the voltmeter demonstrates no voltage differential exists between node 5A through E and node 5F through J. Finally, here's one more way of incorrectly taking a voltage measurement that yields a false reading that can be misinterpreted if you're not paying close attention. Again, consider the previous circuit where an open exists between the power supply positive connection landed at node 2A through E and one terminal of the nominal 200 ohm resistor at node 5A through E. Again, voltage is dropped across a component only when current flows through it. No circuit exists, no current flows, and the resistor will not experience a voltage drop. This being said, a voltage rise still exists across the terminals of the source. If a technician takes a voltage measurement not across the terminals of the resistor, as would be required to measure voltage dropped across the resistor, but rather across the open from node 2A through E to node 5A through E, the voltmeter measures a 5 volt differential across the open. Rather than reading the voltage dropped across the resistor as desired, this would be equivalent to measuring the unloaded voltage rise induced by the source. A technician, unaware of the incorrect placement of the voltmeter, might incorrectly assume a 5 volt drop across the resistor, but this is far from the truth. Again, I must remind you that an ideal voltmeter is modeled as an infinite resistance through which no current will flow. The inclusion of the voltmeter does not complete the circuit, and this placement is not measuring the voltage drop across the resistor, but rather the voltage differential across the open. With an open in the circuit, no current exists, and no voltage is dropped across the resistor. Be on the lookout for incorrect placements of measurement probes. Again, a complete circuit must exist and current must flow through an element if there is to be any voltage dropped across it and power delivered. Alright, that's about it for today. See, I told you it'd be brief. We'll be making use of DC voltmeters in later lectures. In conclusion, this lecture introduced the DC voltmeter function on the digital multimeter. We use the function, leads, range, and placement checklist to place the DMM in DC voltmeter mode, and use the DC voltmeter to measure the voltage rise induced by a source and the voltage drop across an element inside a circuit. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.